Okay, let's take a look now at some of the basic properties of the sets of greatest common divisors and least common multiples. First item is something I'm going to leave for you to prove. If an integral domain R has the property that every pair of elements has the greatest common divisor, then every non-empty finite set of elements has the greatest common divisor. And in fact, this formula holds. The GCD of A, B, and C is the GCD of A and B together with C. So we can build this GCD one step at a time in two steps. This generalizes and also applies to least common multiples. Now, we did run into some difficulty, you might say, with sets of common divisors, and could say only that this was an inclusion and it might be proper. For greatest common divisors, things are more pleasant. Let R be an integral domain and A finite non-empty subset of R, let little r be an R. If the GCD of RA is non-empty, then we have this nice formula. But this is required. This need not hold. If GCD of RA is empty, we might have GCD of RA empty, but GCD of A non-empty, therefore R times that would be non-empty. And in fact, that we saw in the previous example. At the end of the example, I commented on that, and I said we'd be referring to it later. Now we are referring to it. For least common multiples, we have a nice simple formula. No existence requirements here. Okay, so how do we prove part one, this formula, assuming GCD of RA is non-empty? Well, if X is a GCD of RA, then because R is a common divisor of RA, R obviously divides anything of the form R little a, we have R divides X. So there is an element D for which RD equals X. And that's in the set of greatest common divisors of RA. It follows that D is a common divisor of A. Moreover, if E is also a common divisor of A, then RE is a common divisor of RA, and so RE divides a greatest common divisor, RD. And therefore E divides D, which shows that D is in fact more than just a common divisor of A, it's a greatest common divisor of A. So, in summary, if X is a GCD of RA, then X belongs to this set, R times GCD of A. Another way to say that more elegantly is we have this set inclusion. However, this is an associate class in R, and therefore, and non-empty, we're assuming it's non-empty, therefore this is non-empty, and this is also an associate class. R times GCD of A is an associate class. I'll leave that for you to demonstrate. Well, two associate classes are either disjoint or equal, and so these are in fact equal. As for the least common multiple case, we have this formula, and so since these two sets are equal, their subset of least elements is the same. the least elements of this side, of course, is the LCM of RA. What are the least elements here? Well, multiplication by R preserves divisibility, and so the least elements here are in fact R times the least elements in A, something you should think about. And so in fact we have equality with least common multiples on both sides, even if the sets are empty. So here's the summary. Assuming that the GCD of RA is non-empty, we have this nice formula. It need not hold if the GCD of RA is empty. This side could be non-empty still. And we have the nice formula in the case of least common multiples. Well, this brings up an issue related to primeness and irreducibility. We saw in an earlier theorem, 4.5, that in all integral domains, prime elements are irreducible. But the converse need not be true. Primeness is a stronger condition than irreducibility. We also saw that in a principal ideal domain, the two concepts are equivalent. This is why sometimes in the realm of integers, prime elements are identified as irreducible. They have no factors other than one in themselves, a positive and negative one in themselves. In any case, where else might it be true that prime and irreducible are equivalent concepts? Well, suppose that in an integral domain, R, we have x divides AB, and that x and A are relatively prime. It's natural to wonder whether then x has to divide B as it does in the integers. Well, we have x divides AB, but we also have x divides XB. Therefore, provided this greatest common divisor is non-empty, some of these exist, x divides the greatest common divisor of AB and XB, and because of this assumption we can factor out the B, but x and A are relatively prime, so this is B R times a set of units of R, so x divides B. Moreover, if x is irreducible, and x divides AB, but x does not divide A, then x and A are relatively prime because x is irreducible, so the previous situation applies and x divides B. This is the primeness condition on x. So this means that irreducible elements are also prime, and so the two concepts are equivalent. Okay. Theorem, this is known as Euler's lemma for integral domains. R is an integral domain, x, a, and b belong to R, and assuming that this GCD set is non-empty, then x divides AB, x and A relatively prime implies x divides B, and x irreducible, x divides AB, x does not divide A implies x divides B, and now this is an annoying issue, this requirement of existence, but in a GCD, which by definition is an integral domain in which all greatest common divisors exist, we can say that an element is irreducible if and only if it's prime. Okay, let us now consider existence of greatest common divisors and least common multiples. Frankly, almost anything is possible. Anything is possible with one exception. The ring of integers shows that every pair of elements has both a GCD and an LCM. That's the nicest possibility. We will give an example in a few moments showing that an integral domain can have pairs of elements that have neither a GCD nor an LCM. That's the worst possible case. However, this is the one exception to anything goes. If a pair of elements has an LCM, it will have a GCD, and I will demonstrate that for you shortly. If a pair of elements has a GCD, however, that does not imply that they have an LCM. So anything goes except for one situation. LCMs imply GCDs. So first, an example in which there are pairs of elements with no greatest common divisor and no least common multiple. Quadratic domain. We looked at in example 4.6 has this factorization of 21. All four factors are irreducible. No two are associates. Therefore, they're pairwise relatively prime. Now, what I'm about to do works in more generality. This is an example of a situation where R is an integral domain and there is a factorization of the form xy equals zw where the factors are irreducible and no two factors are associates. So we'll work with that general context. To see that xy and xz have no greatest common divisor, suppose to the contrary, that this is non-empty. Since any two of these four factors are relatively prime, we can write x is contained in the set x times GCD of yz. This is the units, contains the element 1, and if we're assuming this is non-empty, we have our nice formula, x goes inside. But also, z is in z times GCD of w and x. And to get the z inside, all we have to do is notice that zw equals xy. So these two sets are the same, so the formula works. So x and z, being in the same associate class, are associates, and that's false. So x, y, and xz have no greatest common divisor. To see that these two elements have no least common multiple, again, suppose to the contrary that this set is non-empty, then we have this equation, no, it worries about existence. And since we're assuming this is non-empty, we know this is non-empty. So take an n in the least common multiples of y and z. This element is a common multiple of y and also a common multiple of z. And so we have y divides n because n is a multiple of y, and because of what I just said, n divides xy. So n equals ry and xy equals sn for elements r and s in the ring. But then xy equals sn equals sry, and so x equals sr. but x is irreducible, so one of R or S must be a unit. If R is a unit, then looking here, N and Y are associates, which means Y is also a least common multiple of Y and Z. No, because Y is not a multiple of Z. Y is irreducible. Z is not a unit. If S is a unit, then looking here, XY is an associate of N, so XY is also a least common multiple of Y and Z, but YZ is a common multiple, so XY divides YZ, which implies that X divides Z, also false. So Y and Z do not have a least common multiple. There is no N. And so we have a contradiction, and so neither do XY and XZ have a least common multiple. So there we have two elements in this quadratic domain that have no least common divisor, greatest common divisor, no least common multiple. Here is an example of an integral domain in which there are pairs of elements that have a greatest common divisor but no least common multiple. R is the subring of the integral domain consisting of the integer polynomials. A polynomial is in R if its coefficient of x is even. So take the elements a equals 2, b equals 2x. These are irreducible. Be careful here. You have to stick carefully to the definition. 2x is not 2 times x, because x does not belong to R. Its coefficient of x is not even. So this is in fact irreducible in R. So the GCD of A and B is a set of units. On the other hand, to see that A and B do not have a least common multiple, observe that 4x and 2x cubed are common multiples of 2 and 2x. So, a least common multiple of 2 and 2x will have to be a common divisor, have to divide both of these. But what are the divisors of 4x? There are 2, because we have 2 times 2x, and so 2x times 2, and 4x, and their associates. Nothing else. 4 is not a divisor because the other factor would be x, which doesn't belong to R. Only positive negative 2 and positive negative 2x divide the other element, 2x cubed. But none of these is a common multiple of 2 and 2x. So A and B have no least common multiple. They have greatest common divisors, units, but they have no least common multiples. One thing to note here, because it will come up very soon, is that the only, at least up to associate, the only common multiples of 2 and 2x that divide the product AB, which is 4x, are positive and negative 4x. Got a little issue here. So while it's true that the least common multiples of 2 and 2x are empty, there are none, if we restrict attention only to the set of common multiples of these elements that divide their product, we get a least common element. Okay. So, in some sense, considering all of the common multiples of two elements is too big a set. If we restrict attention to the common multiples of two elements that divide their product, we get a more well-behaved set. And in this case, it does contain a least element in any case. So let us conclude our rather lengthy discussion of divisibility in integral domains by taking a look at greatest common divisors and least common multiples in principal ideal domains. In principal ideal domains, we've seen that there's a connection between divisibility and the structure of principal ideals, and those are all the ideals, in fact. In particular, D divides A if and only if the ideal generated by A is contained in the ideal generated by D. Now, if A is a non-empty subset of R, then there is an element D in R for which the ideal generated by A is the same as the ideal generated by D, because all ideals are principal. So if little a is in the set A, then the ideal generated by little a is contained in the ideal generated by little d, and so D divides A, and therefore D is a common divisor of the set A. Moreover, if E is a common divisor of A, then E also divides D, that you need to check, and so D is a greatest common divisor of A. So the generators of the ideal generated by the set A are greatest common divisors of A. And conversely, if E is a greatest common divisor of A, and A is generated by, the ideal A is generated by the ideal D, then D is also a greatest common divisor of A. And so E and D are associates, and therefore they generate the same ideal, and so the ideal generated by E is the ideal generated by A. I mentioned this before, but I'll remind you that all these corrections will be taken care of by the time I post the book on my website. So, in principal ideal domains, every non-empty set of elements has a greatest common divisor, and so a principal ideal domain is in fact a GCD domain, and therefore also an LCM domain. Suppose now that D is a greatest common divisor of A. Then D is certainly in the ideal generated by itself, and that's the ideal generated by A, so there exist elements A1 through AN in the set A, for which D is a linear combination of those elements. The R's, R1 through Rn, are elements of the principal ideal domain, but they are actually relatively prime. Not pairwise, but just relatively prime. Because if S is a common divisor of these coefficients, we can write each coefficient R sub I as S times R sub I prime, factor out the S, that shows S divides D. Let's say we'll call that quotient D over S, we'll call it D prime. We can cancel S from both sides, and we have this equation telling us that D prime also lies in the ideal generated by D. So D prime divides D, but this tells us that D divides D prime, And so D and D prime are associates. And therefore S is a unit. So the coefficients are relatively prime. They have no common factors other than units. And in conclusion, we have this theorem. R is a principal ideal domain. If A is a non-empty subset of R, then the greatest common divisors of A are the generators of the ideal generated by A. If D is a greatest common divisor of, these X's should be A's. Sorry for these typos. And so if D is the greatest common divisor of A, then there exists elements A1 through AN, and that belong to capital A, and R1 through Rn in R, for which D is a linear combination, and the coefficients are relatively prime. This is Bezo's identity for principal ideal domains. Elements A1 through AN are relatively prime if and only if they generate the entire ring, the entire principal ideal domain, or equivalently, if and only if there exist elements R1 through Rn for which the linear combination with those coefficients is equal to 1. That should look familiar. If you've studied my other courses, we used Bezo's identity quite often for integers and mostly for integers. If A is a non-empty subset of R, then M is a least common multiple of A if and only if the ideal generated by M is equal to the set of common multiples of A, and that's the intersection of the principal ideals generated by the elements of A. Finally, for finite sets, and I think I'll change that to an A also, D is the greatest common divisor of these elements if and only if D is the sum of the principal ideals generated by the elements. Or, in other words, A is the ideal generated by those elements. M is a least common multiple of the elements A1 through AN if and only if the ideal generated by M is the intersection of the principal ideals generated by the individual elements. I'm leaving you to finish this proof. We've taken care of the first case, and you can prove 2 through 4. So that concludes our rather detailed look at divisibility and integral domains. It's quite a lot of material. It's a bit abstract. It may take several readings or listening to the video several times if you are interested in really absorbing this. If not, you can survive the rest of the course anyway. Well, to complete this chapter, I want to discuss with you a construction known as the field of fractions of an integral domain. The integers, as you certainly know, fit very nicely into the field of rational numbers. As a matter of fact, rational numbers are often defined as quotients of integers with non-zero denominator. Well, the story is actually a little more complicated than that. The problem is that if A and B are integers and B is non-zero, and if R is a non-zero integer, then distinct fractions, A over B and RA over RB, are the same rational number. And that's something that has to be dealt with carefully in defining the rational numbers. In mathematics in general, the way to define new objects, such as rational numbers, by identifying distinct objects, such as these fractions that we're talking about, from a given set X, is to define an equivalence relation on X. Because equivalence relations capture the essence of equality, in particular, reflexivity, symmetry, and transitivity. Once a suitable equivalence relation has been defined on the set X, then we get a partition of X, as shown here. And we can proceed in one of three ways. And let me show you those ways for the construction of the rational numbers. To define the rational numbers, we first define an equivalence relation on this set. This is our set X. Z cross Z prime, where Z prime is the set of non-zero integers. And the equivalence relation is defined by saying that the ordered pair AB is equivalent to the ordered pair CD if AD equals BC. And if you write these as fractions, you can see we're comparing the cross products. Then the equivalence class containing a given ordered pair AB, if A and B are relatively prime, is just the set of ordered pairs RA, RB, where R is non-zero. Now we have three choices for defining rational numbers. Looking at this picture, we could pick a single element from each equivalence class and declare those as the rational numbers. If we wanted to do that, there'd be an obvious choice for the individual elements in each equivalence class, namely the ordered pairs AB, where A and B are relatively prime and B is positive. We could have chosen A to be positive, it doesn't matter, but one or the other. We have to choose and stay with that choice. And we generally write the ordered pair AB as a fraction, A over B. There's a drawback to this, so in fact there's a couple. First, for example, the quotient 2, 4 is then not a rational number because the ordered pair 2, 4, the elements 2 and 4 are not relatively prime, so it doesn't fit the definition. And that's not really what we want. The second problem, and it's far worse than that, is that this approach depends on being able to identify a special element from each equivalence class. So when we start talking about integral domains in general, that's going to be either very difficult or impossible. So the first option here is really not very good one. Second option would be to simply think of every member of a given equivalence class to be the same rational number. So the ordered pairs 1, 2 and the ordered pairs 2, 4, or in the more usual notation 1/2 and 2/4, are simply declared to be the same rational number because they're equivalent. This is often the most practical choice when we generalize to arbitrary integral domains, but there are issues, of course, here, and that is that distinct fractions are the same rational number. That causes issues with well-definedness. They're not insurmountable by any means, but they need to be addressed. A careless disregard for that can lead to serious problems. Here's a very trivial example that probably would be spotted immediately. take the numerator map defined by f of the fraction ab as a is garbage. It's not a function. It's not well defined. F of 1/2 is 1. F of 2/4 is 2. So there's an immediate problem of not being well defined. But there may be other cases where the issue is more subtle. Third choice is to define the rational numbers as the equivalence classes themselves. So this would, for example, be a rational number, the equivalence class containing the ordered pair 1, 2. And we're going to make that choice, so we're going to simply write that as the fraction 1/2, 1/2. This approach doesn't suffer from the problems of choice number 1, but still requires attention to the issue of well-definedness because equivalence classes generally have more than one representative. So our choice that we will generalize to arbitrary integral domains is to define the set of rational numbers as the set of equivalence classes of ordered pairs. And the equivalence class that contains the ordered pair AB will be denoted by A over B, or the fraction A over B. So fractions are sets. They're equivalence classes. The next step would be to define the ring operations on this set. But we're going to generalize to arbitrary integral domains in a moment, and we're going to define the ring operations there, and they're going to look identical to the way we define them here, so we'll postpone that. Nevertheless, once that is done, the rational numbers will be a field, and they will contain a ring isomorphic copy of the integers. So the integers, this copy will be a subring of this field. The equivalence class containing the order pair n1, or in other words, n/1, n over 1, this is the copy of the integer n that lies in Q. Q, in fact, is the smallest field containing a copy of the integers. So, let's now do this for an arbitrary integral domain R. It's essentially the same, oops, little spelling error, as it is for the rational numbers. And we've done everything except define the ring operations. So what we're going to do is construct a smallest field containing an isomorphic copy of the integral domain R. This is called the field of fractions of R, or sometimes the field of quotients of R, but it is not a quotient field. That object does not exist. We'll discuss that. I think I did discuss that already, but we'll do it again in the next lecture series. I'm going to denote the field of fractions by fract R. So we start, again, R prime is the non-zero elements of R. We take this set of ordered pairs, R cross R prime, define an equivalence relation exactly as we did for rational numbers, or for integers. Define the fraction AB, where B is not 0. The A and B belong to R, B is not 0, to be the equivalence class containing the ordered pair AB. So it looks like this. As far as equality of fractions, or in other words, equality of equivalence classes, these two equivalence classes are equal if and only if they overlap. And that will be the case if and only if the order pair AB is equivalent to the order pair A prime B prime. Or put another way, AB prime equals BA prime. The cross products are equal. Excuse me, still have a cold. So, because of this definition, we get the usual property of fractions, at least fractions of quotients of integers, stuff like this. Now we can define the field operations, and taking our cue from the rational numbers, we would define addition and multiplication of fractions this way. Again, these are equivalence classes, so there's an immediate concern as to whether these are well defined or not. And I'm going to leave that for you to sort out. They are well defined, but it's an important exercise for you to show that these operations are well defined. I'll also leave it for you to check associativity, commutativity, and distributivity. The additive and multiplicative inverses look like this. The negative of A over B is negative A over B. There's some spelling errors. All this will be fixed by the time I post the book for sale on my website. And as to multiplicative inverses, if A is not 0, the numerator, then the inverse of A over B is B over A. Pardon me. Under these operations, fract R is a field. Now, the map sending R to fract R that sends little r to little r over 1 is a ring embedding. Here is the preservation of subtraction, preservation of multiplication, preservation of the identity. I'm not going to go through those because it's something I think you should do as good practice. Here is the demonstration that kappa, this function here, is injective, so it is a ring embedding. Therefore, kappa of R is isomorphic to R as rings. It can't be as fields because R is not a field necessarily. And we can identify the elements little r and r with the fractions r over 1. Everybody does that. Everybody thinks of an integer as a rational number. But in truth, there's a little fudge there. But we're going to do that just like everybody else. Finally, fract R is, I said the smallest field, I should say a smallest field because isomorphic fields would also work, is the smallest field containing R, and again we're making that little fudge, as a subring, or as shown here, if any field F contains R, then it also contains an isomorphic copy of fract R. And that contains R and is contained in F, sits in between. As to proof for that, we just define a map from fract R to F by lambda of A over B is AB inverse. This makes sense. B is non-zero, and therefore in F, because it contains a copy of R, B is in F, so it has an inverse. If little r is in R, then lambda of little r, which is lambda of R over 1, is in fact equal to R. So lambda is the identity on R. So R is mapped to itself. Okay. We are doing a little bit of the usual fudge here. To be more precise, we would have to say this, suppose F contains an isomorphic copy of R. This is also an isomorphic copy of R. And we'd have to fix this map lambda, but I'm going to leave that for you to do if it's something you want to do. It sounds slightly unpleasant, but is not terribly important. This map lambda then is a ring map. There's the multiplication, mapping the identity to the identity. It's injective, and so F does in fact contain an isomorphic copy of fract R that contains R. And this is a summary of what we've discussed. So the construction of the field of fractions of an integral domain is very important. I'll give you a couple of quick examples. We just saw the field of fractions of the integers is the rational numbers. That alone is important enough to make this construction worthwhile. The field of fractions of f square bracket x, a polynomial domain, F is the field here, is the field of rational functions. And the field of fractions of the Gaussian integers is the Gaussian rationals, Q plus Qi. In the next chapter, we will discuss factorization in integral domains. We've spent quite a bit of time with divisibility in integral domains. We'll discuss factorization and unique factorization. Factorization in particular into irreducible, product of irreducible elements. We will see that those integral domains that have the property that every element that's a non-unit, non-zero non-unit, can be written as a product of irreducible elements are quite well behaved, especially when that representation as a product is essentially unique. Unique up to the order of the factors and up to associativity, not associativity, up to associate. So you can replace factors by their associates. So it's essential uniqueness. In the context of essentially unique factorization, some of the issues that we encountered when we talked about divisibility go away. Quadratic domains are not, in general, unique, do not have the unique factorization property. They have the factorization property, but it's not unique. Okay? And that's where we ran into difficulties with divisibility.